Welcome to the Thermal Blueprint, a video exploring the physics, mechanics, and engineering behind modern climate control. This is a macro to micro primer on HVAC systems. HVAC stands for heating, ventilation, and air conditioning. The primary outcomes of these systems are controlling temperature, humidity, air quality through filtration, and air movement or distribution. Every mechanical system is designed for thermal comfort. Key factors include air movement, fresh and clean air, low noise levels, and adequate lighting. Target temperatures are typically 78 degrees Fahrenheit for summer and 68 degrees for winter, with a relative humidity between 30 and 60%. Heat always flows from hot to cold via three mechanisms: conduction, convection, and radiation. HVAC systems deal with all three, such as heat transfer through a wall by conduction, cold air mixing with warm air by convection, and solar heat passing through windows by radiation. The cooling load is the total thermal energy the mechanical system must extract to maintain balance. This energy comes from various sources, including conduction through the roof, solar radiation, outside air infiltration, and internal loads from people, lights, and equipment. The Psychrometric Chart maps the thermodynamic properties of air. The x-axis is dry bulb temperature, and the y-axis is moisture content. Knowing any two conditions of air allows all other thermodynamic properties to be found on this graph. The entire HVAC infrastructure exists to plot indoor air into the Goldilocks zone on the chart. Building loads, weather, and occupants constantly push the air state outward, and mechanical systems pull the ambient conditions back into this zone of thermal comfort. The refrigeration cycle uses a compressor, condenser, expansion valve, and evaporator to move heat. This diagram illustrates how the refrigerant transitions between high and low pressure sides and hotter and cooler states as it cycles through the system. The main components include the compressor, which pumps refrigerant, the condenser, which rejects heat out of the system, the thermal expansion valve, TEV, which controls refrigerant flow, and the evaporator, which absorbs heat and provides cooled air. This slide provides key HVAC conversion formulas. The unit of refrigeration, 1 TR, equals 12,000 BTU/HR, or 3,000 kCAAL/HR. Also included are the formulas for converting between Celsius and Fahrenheit. The scale of solutions continuum ranges from small-scale residential systems like window ACs to medium commercial package AC systems, and finally to industrial/hyperscale air handling units using DX or chilled water, increasing in cooling capacity and complexity. Architectural configurations scale with building demand. DX systems use refrigerant for direct expansion and are best for small to medium buildings. Chilled water systems use water as a secondary refrigerant and are ideal for large cooling needs in industrial processes or hypermarkets. The building load and selection radar shows key factors influencing system selection, including ambient conditions, occupancy levels, lighting and equipment load, and client budget, along with building-specific factors like floor layout and glass exposure. The engineering workflow involves 4 steps. First, calculate strict cooling load requirements. Second, select the appropriate system type. Third, design the distribution networks. And fourth, evaluate the final integrated mechanical system. The ultimate goal of engineering is invisibility. The success of a modern HVAC system is measured by a single metric: the occupants never notice it's there. This is the physics of perfect climate control.